Hey guys, welcome back. For the next several videos, I'd like to talk to you about some of the basic rules in probability. Now, probability is a field that you can study for the rest of your life, so I'm not going to pretend to be thorough here. I do just want to get you started on how to think about probability. So for this lecture, I'd like to do a very brief introduction, and I'll follow it up with ever more slightly increasing in detail presentations on probability. So where do we start? We should always start with some definitions. And the key definitions for today are a random experiment or a random variable and a sample space. So we need probability to understand random events. And so a random experiment or a random variable is going to be one whose results we don't know in advance. And we're going to have to try to guess like how likely is a particular outcome. Now, the sample space is going to be the set of all those possible outcomes. And ideally, we'd like to be able to assign probabilities to every single one of those things in the possible set of outcomes in the sample space. So what is a probability? It's going to be a number between a 0 and 1 that measures the likelihood of an event. Now, 0 and 1 is the same thing as 0% and 100%. And most people think in terms of 0%, 100%. Statisticians like to feel important and obscure, and so they go, it's a number between 0 and 1. But really, it's between 0% and 100%. And when we say that the probability is equal to 0, that means it's never going to happen. And if it's probability 100%, then guarantee it's going to happen. In fact, it's not even a question of probability anymore. It's guaranteed. So the simplest type of probability, you can think of it as if we were to repeat an experiment over and over again, how many times would a particular event happen? Now, you can't always repeat an experiment. If we were flipping coins, you can flip a coin 1,000,000 times. If we're talking about, what is the probability that a particular person will win the next presidential election, it's not like you can repeat that exercise 1,000,000 times. In fact, there's some kind of debates on whether we can actually talk about probability in that case. But brushing that aside, let's just think of probability as how many times, if we repeated an experiment 1,000,000 times or an infinite number of times, what proportion of those times would a particular event happen? Finally, some notation. We're going to be talking about the probability of a particular event happening. So the probability of a particular thing. So probability. And our variable is going to be denoted with an x. So our experiment is x. Experiment x. Now, the particular outcome of that experiment we will denote with a lowercase x. All right. So our experiment might be coin flips. And a particular outcome might be that it comes up heads. In which case, we could, talk about what is the probability that our coin flip comes up heads. Or if we don't want to commit to a particular value, we could just use a little lowercase letter just to denote, one of the many possible outcomes that this experiment could have. And if we really want to conserve notation, we'll just say, what is the probability of heads? Or what is the probability of that one particular outcome? And we won't always write out, what is the probability that the random variable big X takes on this particular value little x? Because that just kind of gets cumbersome. So, okay, so we can think of a probability distribution, right? It is a list of all of the possible things that could happen and what their probabilities are. So let's just say we flip a coin. Now, what is our sample space? We defined our sample space to be the set of all possible outcomes. If you flip a coin, it's only heads or tails. So that's our sample space, right? It's heads or tails. It's that set. And if you flipped coins before, you know that the probability of heads is 50% and tails is 50%. Right? And notice this statistical preference for numbers between 0 and 1 rather than in terms of percents. Okay, and when we put this into a table like this is called a probability distribution table. All right, so here's our little table. And then here we have little x could be heads or little x could be tails. Right, and then this is the whole set of probabilities. And we know we have an exhaustive list of probabilities because when we add them up, we get 1 or 100%. So we've covered all of our bases. Now, the simplest kind of questions dealing with probabilities, we can classify them as classical probability. Now, this is a whole set of types of experiments where the outcomes are equally likely, and then we can just kind of use those equally likely pieces to kind of calculate different second stage probabilities. It's best if we go to an example. So let's say we toss 2 coins, right? And what is the probability distribution for the number of heads? Okay, so we flip 2 coins. What is the sample space? What are all the possible outcomes? We could have 2 tails, we could have 2 heads, we could have head tails or tails heads. But we're counting all of the number of heads. So really, our sample space is no heads, 1 head, or 2 heads. And now, what is the probability associated with each of these outcomes? So we can just count now, right? So what is the probability of no heads? Well, only 1 out of these 4 outcomes came up that way. So 1 out of 4 chance. What about if it only comes up 1 heads? Well, that would be these guys in the middle here. Head tails and tails heads. That's 2 out of the 4. So 2 out of 4 is the same as 1/2. And finally, what is the probability that we get 2 heads? That's this guy here. That was 1 out of the 4 possible outcomes. So that's 1 out of 4. Now, I have to admit, this is a bit circular. I'm like teaching you about probability, but presuming that some key events are equally likely, right? That tails tails is equally likely as heads tails is equally likely as this, and that's why we could just figure out, 1 out of 4. I admit that from the get-go. We can drop that assumption, but let's not yet. Let's just start with a simpler example like this classical probability, and then we'll go from there. Essentially, when probability was discovered, was invented, it was at the request of a rich nobleman who hired a couple of statisticians so he could figure out how to bet properly. And so we're going to actually follow this kind of statistical thinking where, coins are equally likely heads or tails, or dice are equally likely 1 through 6, and so forth. So we'll drop that later, but for now, let's go with it. So another example, let's say that we tossed 3 coins and we wanted to know what the number of heads were. Procedure is familiar, hopefully by now. You just list out all the possible outcomes. And so at the top, I've got all the ones that start with H's. So we've got 3 heads. We got 2 heads followed by a tail. Heads, tails, heads, and heads, tails, tails. And then finally all these other options here that start with tails. Okay, so all the possible outcomes then for our random variable are 0 heads, 1 head, 2 heads, and 3 heads. And what's the probability of 1 head? All right, we got 8 outcomes. 1, 2, 3, 4 on the top, 5, 6, 7, 8. How many just came up with 1 H in there? Those all have H. Here's 1 H. Here's 1 H. And here's 1 H. So 3 out of those 8 outcomes. What about no heads? Okay, well, I can tell you right now, there's only one of those. That's this guy here. That was 1 out of 8. What about 2 heads? All right. So 2 heads. This is 1. This is 1. And this is 1. That's 3. So 3/8. And finally, what about having 3 heads? That's this guy up here. Notice I had already marked off each of these eventualities. There was only 1 left, so it had to be 1/8. And sometimes it's nice just to count and verify. Okay, so that's a 1 right there, 1/8. And let's check that everything adds up to 100%. We have 1/8 plus 3/8, that's 4/8. And then another 1/8 plus 3/8 is another 4/8. So that's a half plus a half. That's 1, or 100%. So we're good. Okay. Let's consider something with more than just 2 outcomes for the coin flip. What about a dice? Or I guess a singular, a die. What's the probability that we get a 2? So our sample space now has 6 outcomes because there's 6 faces to a standard dice, standard die. We're not playing Dungeons and Dragons here. Standard dice, 6 faces. What is the probability that we roll the dice and we get a 2? Okay, well that's only 1 out of these 6 outcomes. So our probability is 1/6. What if we rolled that die, and rather than asking if it came up a 2, what if we asked if it came up even? Okay, so now there's several different ways this could happen. It could be that it comes up as a 2, or it comes up as a 4, or it comes up as a 6. And so we need to, well, we could just count, right? So the probability that it comes up even is 3 out of the 6. So in other words, 50%. Kind of like a coin flip. Notice that what we're looking at now is a slightly different kind of question in statistics, where we're looking at the union of a couple of different events. So it's 2 or a 4 or a 6, rather than just a particular outcome. All right, so with less information on the screen now, what's the probability that you roll that die and it comes up less than 5? Now, I'll show you a couple different ways to do this one. I guess the simplest way is just to list out all of the possible outcomes. For each of these, we've got a probability. So 1/6 chance for each of these. It's a fair dice. A simplifying assumption. Could be, maybe we're in a shady part of Las Vegas. But what's the probability that it's strictly less than 5? So it's going to be one of these outcomes. Right? So let's just add them up. So we have 1/6 plus 1/6 plus 1/6 plus 1/6. We have 4/6. So 4 out of 6 probability. Now that's one way to do it. Another way of doing it is to realize that you just have two ways that you could go wrong. And so, so what must this larger sum be equal to? Well, it's got to be 100% minus your 2/6%. So 1 minus 2/6, and that gives you your 4/6. Okay, so throughout this slide deck, I've basically been presuming that that the probabilities that we're interested in can be kind of thought of as the sum of a bunch of equally likely events. So that, you know, the probability of rolling a 1 on a 6-sided dice is the same as the probability of rolling a 2. It's the same as rolling a 3. And they're all 1/6. And so what's the probability of a 1, 2, or a 3? Then it's got to be 3/6 or a half, right? So I can think of more complicated probabilities as the sum of a bunch of very simple, equally likely events. And just splitting up the sample space like that and just adding really facilitates that. It's useful. It's a nice little trick. There's more to probability than that, and I don't want to leave you with the wrong impression. Just counting possibilities can lead you astray. So, you know, is it going to rain tomorrow? Well, either it will or it won't. There's only really two outcomes. That doesn't mean that the probability of rain is always 50-50. We will look at more complicated kind of probability scenarios, but you'll have to tune in to some more videos to see that. Thanks.